For this lesson, we're going to have the normal distribution, and we're going to have the normal distribution with mean equal to 0 and standard deviation equal to 1. So in order to standardize a normal random variable, so if your distribution does not have the mean and the standard deviation equal to 0 and 1 respectively, what we're going to do is to use the standardizing formula. Z is equal to x minus mu over sigma. So that is, if the expected value is mu and the variance is sigma squared, we use this formula to convert the distribution to have a mean of 0 and a variance equal to 1. Example. Suppose that the current measurements in strip of wire are assumed to follow a normal distribution with mean is 10 and variance is 4. So meaning sigma would be equal to 2 milliamperes. What is the probability that the measurement exceeds 13 milliamperes? So that would be the probability that the measurement is greater than 13. So let x denote the current in milliamperes. The requested probability can be represented as the probability of x greater than 13. So we convert 13 into a z-score of 13 minus 10 over 2. So that would be 3 over 2 or 1.5. So we will now be having p of z greater than 1.5. So since it is greater than an area to the right, what we do is to get the complement. Since the total area is 1, so that would be 1 minus the area to the left. So 1 minus p of z less than 1.5. If you're looking at the table, p of 1.5 is 0.93319. So therefore, the requested probability is 0.06681. So if the distribution is originally having a standard deviation of 2, we can convert that into a distribution with a standard deviation of 1. Here, the mean is 10. For this one, the mean of z is 0. So, to standardize or to calculate the probability, suppose that x is a normal random variable with mean mu and variance sigma squared, then the probability that the random variable x takes the value less than or equal to x is equal to the probability of x minus mu over sigma, which is z, less than or equal to x minus mu over sigma, which is the probability that the random variable z takes a value less than or equal to z. So where z is the standard normal random variable and z is equal to x minus mu over sigma, the z value obtained by standardizing the random variable x. Another example, what is the probability that the measurement is between 9 and 11? So it would be as an x. So we're looking for the probability that x is between 9 and 11. So that would be equivalent to a z with the value x minus mu over sigma, x minus mu over sigma. So that would be p of 0.5 minus p of negative 0.5 because we're looking for the area in between. So this is p upper and then this is p lower. So we subtract their probabilities. So the answer would be 0.38292. Determine the value for which the probability that the current measurement is less than this value is 0.98. So the probability or the area is 0.98. Below this value, we have a probability of 0. The probability is 0.98. Less than this cutoff, the area is 0.98. So first, we inspect what would give us a 0.98 area, and the closest would be 2.06. So with that 2.06, we use x minus mu over sigma equal to 2.06, and from there you can compute for x, which is 14.1 milliamperes. These are some of the additional problems you can solve, and we're going to discuss this if you have questions on doing this. So the line width of a semiconductor manufacturing is assumed to be normally distributed with the mean mu is 0.5 and standard deviation sigma of 0.05. What is the probability that a line width is greater than 0.62? So this is the probability of x greater than 0.62, or the probability of z greater than 0.62 minus 0.5 over zero point zero 0.05, or 1 minus p of z. What is the probability that a line width is between 0.47 and 0.63 micrometer? So this would be phi of 0.63 minus 0.5 over 0.05 minus phi of 0.47 minus 0.5 over 0.05. Next is the line width of the 90% of the samples is below what value? So if phi of z is 0.9, um, that would give us, I think, uh, most probably 1.28. So if z is 1.28 with mu zero point 0.5 and sigma 0.05, you can compute for x. The life of a semiconductor laser at constant power is normally distributed with a mean mu is 7,000 and standard deviation sigma is 600. What is the probability that a laser fails before 5,000 hours? So we're looking for the phi of 5,000 minus 7,000 over 600. What is the life in hours that 95% of the lasers exceed, and so on. So if 3 lasers are used in a product and they are assumed to fail independently, what is the probability that all 3 are still operating after 7,000 hours? So this is now a binomial distribution. These are some of the references used for this study.